Hello everyone. In this video, I am going to share with you about a central limit theorem. We will discuss about the concept behind, and I'll take up three examples of different category to illustrate this concept. So let us begin with the concept. That what does it mean? Central limit theorem, it states that a sampling distribution of a mean, right, that will always approximate to a normal distribution provided the sample size is sufficiently large. Sufficiently large, here we mean that n should be greater than or equals to 30, right? Now this also states that this result holds true regardless of the population's original distribution. That means might be the parent population is a normal by nature, or it might be uniform, exponential, Poisson, binomial, or any other form. So whatever might be the parent population, but if we pick the samples and we take their mean and start plotting it, so it is called a sampling distribution. So let's say in the first case, here we have considered some population distribution and its corresponding sampling distribution if we plot the means. So for example, in the first graph I have taken, for example, the original population is a normal. So if we start plotting the mean of the samples and we observe that the distribution will behave like normal. So here one important point is that if the population, which is a parent population, if it is originally, let's say, normal, then whether the sample size is less than 30 or more than 30, it hardly matters because it will always be created as a normal. So there is no restriction for the n if it is originally data from the normal distribution, right? So the second here graphically I have tried to explain. Let's say if the parent population is uniform, right, and if we consider the samples and we start finding the mean of the sample and plot it, we observe, and it should be sufficiently large sample greater than or equals to 30, then we observe that the obtained pattern will be normal, right? So if we start plotting means, so here the point is whatever might be the sample, if you pick it and start finding its average and then plotting them, you will always get. So here the plotting is of averages, so averages will have a mean also, so it will always be created a normal pattern. Same you can see from the third case. I took here example of, let's say, the original parent population might be, let's say, exponential, and if we start plotting the averages sample and then we take a average and then plot it, we always get a pattern of the normal, right? And same we can say any other distribution. So if we try to understand that what does it mean, so if we write a notation wise, it means, let's say we are plotting x bars and x bars are behaving normal. That means whenever we say normal, we need two parameter. One is a mean and second is a variance. So always remember that when we find x bars, so mean will be remain as same as the population mean, but the variance will change it from sigma square upon n. So here the difference between the population variance and the variance of the x bars, that will be now sigma square upon n. So from here we can drag some information that mean of the x bars are same as mu, but variance will change. It means the standard deviation, you can say, or a standard error will be sigma upon root n. Now why we are talking about it? Because whenever anything is normal by nature and we want to evaluate it, we always convert it into the standard normal variate to find our problem solving. So here if I want to discuss that how we can gather information associated with it. So let's say if x bar is a mean of a random sample of size n, which is taken from the population with mean mu and variance sigma square, then the limiting form of the distribution, when we convert it into z, is z is equals to x. We always write the variable here, the average minus divided by standard error. So if we see how z look like when I want to solve my problem over x bars, it formula is x bar minus mu upon sigma upon root n, right? So this is one of the very important results, that whenever the query is over x bars, we can use the CLT. Central limit theorem is always applicable whenever we want to find a probability of the averages. And same we can see that since whatever we know that x bar is equals to summation of xi upon n, and that can be replaced as Sn because we are using Sn as a sum of all the samples. So we can say that the result can be also reduced for Sn. The same CLT can be reduced to Sn problem. That means when we are not finding an average but we are finding a sum of the samples. So if my main entity is a sum of the sample, we can say it is also following the normal distribution. Only I have to see that the mean and variance will be modified. Now the mean for the sum will be n into mu. Why? Because we can see it from here. X bar is equals to S upon n. So if I want to find out what is the formula for Sn, it is equals to n into x bar. So from here we can gather that mean for Sn is n into mu and variance is n into sigma square, and from there we can get a standard error, or we can say standard deviation. It is root n times sigma. So in the same manner, if we want to solve questions which are based on sum, we can rewrite our z in the new way, wherein what we need to remember that here my entity are Sn, the mean will be n into mu and the standard error will be root n times sigma. So when we will take up an example, I have consider three category of examples. One is for x bar, second is for Sn, and the third one is where n is to be calculated. So let us see one by one. Let's see the first example. Here the example is the lifetime of a certain brand of electric bulb may be considered as a random variable with mean 1200 hours, standard deviation 250 hours. Find the probability using the CLT, Central Limit Theorem, that the average lifetime of a 60 bulb exceeds 1250, and they have given us all the probability value, because if table is not available and the information of probability is available, we can utilize it. So let us begin with the question. First of all, let's write down what are the given information. So here mu given as a 1200 hours, right? Standard deviation is given as a 250, and in this question the number of pulse for which the query is talking about, so here n is required, so n is given as a 60. Now we want to find out the probability of x which exceeds 1250. So this is our query. Now before switching over to the problem, let us first write down our main entity that we want to convert. Sorry, here it is x bar. So we want to convert z is equals to x bar minus mu, which is mu of the is equals to same mu, which is equals to 1200, and standard deviation of x is equals to standard deviation divided by root n. So here what is a sigma value? So first let us plug in the formula. So we got x bar minus 1200. So here it is 250 divided by root of 60. So we will plug in all the given values here so that only the variable things can be written. So we got in this question our z is written in this manner. Now we can convert it in, switch over to our question. We want to find out probability of x bar which is greater than 1250. It's a continuous, so we can write down greater than or equal to, hardly matters, right? So now the first step is, now here if x bar is my main concern, so when I will subtract 1200 from it and divide it by 250 by root 60, it will convert it into z. So I can replace x bar by z, then my 1250 will be replaced here. So we can write down 1250 minus 1200 divided by 250 upon root 60. Now let us first simplify and see what will be the resultant z value. So when we subtract, that will be 50 upon 250, and we can take a square root of 60 on the top. This and this will get cancelled. Now if I see with the help of calculator, you can calculate it root 60 by 5, which comes out to be 1.54919. So if the table value is given for the 2 place of the decimal, we can write down approximately it will be 1.55, right? So we want to find out this value. So first of all, the best way of doing this question is, let us see how it look like. For example, this is a z, the central value of z is 0, and 1.55 somewhere on the right hand side, 1.55 here, and we want to find out the probability more than 1.55. So let us first see what is given to us. In this question, the probability of z less than or equal to 1.55 is 9394. It means this value given to us is, this is given to us 0.9394. The value which is required is other side of it. So it means if I want to find out my value, I can say from 1, if I delete the value of z which is less than or equals to 1.55, my answer is obtained. So I'm going to delete the given value from the 1 to get my required value. So when I simplify it, I'll get 0.0606. So this is the probability of the given question. So I hope you got an idea. Now the next question I am going to take up, wherein the queries are for SN. SN means they are finding the probability of xi's, right? So let us see what is given. They said these x1, x2, xn are independent Poisson variate with the parameter 2. If Sn is written like that and n is equals to 75, use CLT to estimate the probability of Sn between 120 to 620, and some probabilities are given. So again, I said that CLT can be used for x bar as well for the sum, so we can apply on both way. So let us first write down the given information. What is given in the question? They have given us a mu, and you know in the Poisson distribution mu is the parameter lambda, which is same as 2, and similarly variance, which is again equals to lambda, because for Poisson distribution mean and variance are same, and usually we use the parameter lambda for that. So it means if I am using the notation mu and sigma square for the mean and variance, so whatever might be the distribution, we can put it equals to that, and here it is also 2. So I need a sigma, so it means it is equals to root 2. So sigma is equals to root 2, mu is equals to 2, and now n is equals to 75. What is left? We want to write down my z value. So if I write down my z value, I have already written here, means you can convert your question into x bar also, but I don't think it is required. We can rewrite our formula in Sn. So when there is an Sn, n is multiplied with mu and root n is multiplied with sigma. So we can modify our z. So I can write down that when my variable is Sn, my mean will be n into mu, and my standard error will be root n times sigma. So if I plug in the value for n is equals to 75, mu is equals to 2 divided by root of 75 into root of 2. So when we simplify, my z is converted into 150 divided by, we can write down root 75 and 2 as a root of 150. So that is going to be my z for this question. Now come back to the problem, that what is a query? Query is that Sn lies between 120 to 160. So what we can do here, since I have written my z, so I am going to replace Sn by 120. So when I replace Sn by 120 and subtract it from 150 divided by root of 150, so it will be my conversion of question from Sn to z. So it will be z, and here again replace Sn by 160. 150 is a fixed mean value for it, and this is a standard error for it. So when we simplify it, what we can do, when we simplify, 120 minus 130 will be minus 30 divided by, this will be, I'm writing here, this value will be minus 30 and this value will be 10. And when I divide minus 30 by root 150, I'll get this value as a let's say minus, I'll round up to the place of decimal, so we can write like that. So you can check the values with the help of calculator. Now let us see with the help of diagram that what we are looking for in this question. When we are converting into z, the location of mean for z is at the center as a 0, and minus of 2.45 is somewhere here, and 0.82 is here, and we are looking for the area in between, right? So probability in the continuous distribution is always a area under the curve. So we want to find out. Now this means the upper area z less than 0.82, if I subtract the probability of z less than minus 2.45, my job is done. So we can see from here they have given us the value that when it is a less than minus 2.45, it is 0.0071. When it is less than or equals to 0.82, it is so it is also equal to, so we will go with that. So we are going to plug in the value of the what is that? Yeah, 0.7979. So it is 0.7979 subtract 0.0071, and when we simplify we are getting 0.7908. So that is our answer, right? So you can see from here that sometimes the query can be in sum or in X bar. Both the way we can apply the central limit theorem. Now let us take up the last question, which is finding n. So let's read the problem. They are saying the guaranteed average life of a certain type of electric light bulb is 1000 with the standard deviation 120, right? It is decided to sample the output so as to ensure 90% of the bulb do not fall shortage of the guarantee. Do not fall shortage of the guarantee average by more than 2.5%. So let us first try to convert this statement into the equation. So first of all, let us write down the values. Here the mu is given as 1000. Standard deviation is 1 to 5. They all are the, I'm not writing the units because all are same. And here n is missing. They are saying it is decided to sample the output so that do not fall the shortage of guarantee by more than. So use the central limit theorem to find the minimum sample size. So we are looking for n here. So n is missing. So first of all, what do we mean by 2.5% of the 1000? 2.5% of 1000 is equals to 2.5 by 100 into 1000. That is equals to 25. So let us see the query. If I rewrite this line, to ensure that 90% of the bulb do not fall short of the guaranteed average by more than 2.5%. What does it mean? It means we have to find the probability of average life more than shortage of 1000 minus 2.5% of this 1000. It should be 0.9. It means we have just seen that what is a 2.5 of that? It is 25. It means probability of, actually we are looking for 1000 deleting 25 out of it. It must be equals to 0.9. 90% means 0.9. That means we are looking for x bar should be greater than 975. And that should be 0.9. Now again the same thing. What is our z value here? Z is x bar minus mean. Mean is 1000 here, divided by sigma 125 upon root n. So this is the z value. So I'm going to convert our question into z. So where there is a variable, it will be converted into z variable. Where there is a point, will be substituted in place of x bar. So when I find 975 minus 1000 upon 125 by root of n, it should be equals to 0.9, and when we simplify it we will get it equals to, because when we subtract it I'm getting minus 25, root n will go in the numerator, 125 in the denominator is equals to 0. Area of Z table which can be matching with this point. So let us first see what is given in the question. Question says probability of Z less than 1.28. So let us see, they said probability of Z less than 1.28 less than is equals to 0.9. Now since in our case it is a negative value, so it means if I see the symmetric nature of the normal distribution, it means if this value 1.28, positive size is leaving, left side of the area is given by 1.28 which is having area 0.9, the same scenario can be on the other side, that if the point is 1.28 it can leave the same area 0.9 on the right hand side because of the symmetric nature. So if this is given to us, what is given? Given to us is a probability of Z less than 1.28 is equals to 0.9. So using the symmetric nature of the normal distribution, it means the probability of Z, that means we can write here, probability of Z more than minus 1.28 should be equals to also 0.9. So if we compare these two expressions, we can get that minus root n upon 1 to 5. Sorry, I think I made a mistake here. When we simplify, this is 5. So we are getting here 5. So we are getting minus root n by 5 is equals to minus 1.28. So when I simplify, we are getting root of n is equals to 5 times 1.28. That means root n is equals to 6.4. So we want to find out n. N is equals to squaring both sides, so we get an n. So it is coming out to be 40.96. Because n is a number, so it will be approximately very close to 41. So it is the minimum value for that is n. So we got a n value. That means this condition is fulfilled if n is equals to 41. So I hope you got an idea how to deal with the central limit theorem. Thank you for watching.